You mean we should start? Yes? All right. Well, welcome to your own office. My name is Chris. I was invited by a bunch of people that I met in the Ukraine, at Devox Ukraine, and I talk a lot about Graal, so I'll do that today again. I work for Twitter, obviously, wearing the same shirt again. If you're going to watch, so this is going to be streamed anyway, but any other talk I'm going to mention today, it's all on YouTube, already recorded 1 million times. And you will see me with the same shirt, so you will know it's legit me and not someone else impersonating me. So I work at Twitter, and at Twitter, yeah, this one, it's usually I have to cram in. One demo I can't do today because it doesn't build currently, but you know, we'll skip that one. But I'll go slow today because we have enough time. Usually I have to cram it into 50 minutes, and if I do everything, it takes over an hour. So, but anyway, I'm doing stuff. You can always ask questions in between, and I can multitask to some degree. So, at Twitter we have a VM team, and the VM team used to be rather small, but we grew in size in the last year. Like we doubled. We now have 8 people on the team, and we have about 3 GC engineers, and their job is basically to keep all of our services running in terms of, you know, the GC problems that all the people have. You guys, as far as I know, you have external customers and doing stuff for them, so I'm sure every one of them already had a GC issue at one point, like everyone on this planet did. I'm a compiler guy, so I have nothing to do with that. And there are rarely compiler issues, so I have a lot of free time to do other stuff. And like coming here and talking about things, having free pizza and free beer. So if you want free beer, by the way, I can organize that. Even right now. I've done talks with beer on stage, so if you guys want me to do that, I can do that. I'm not sure how the YouTube streaming, but so I'm a compiler engineer, and I rarely have any support issues. So what we do at Twitter is we brought in Graal, and we are running a bunch of our microservices on Graal, and that helps us reduce cost by a lot. I can, maybe later when I showed you a bunch of stuff, maybe I'll switch over to one of my other slide decks and show you a little bit, but the size of the savings I'm talking about, so you have a rough idea what I'm talking about. But anyway, so I ask a lot of questions today, and the most important question, as always, is who has a Twitter account? Okay, very good. But not all of you. I know. What? Who has a Facebook account? No, don't. If you're going to tweet about this talk, which would be nice because it's streamed and it's kind of live and for everyone to see, tweet about it. Whatever you want to say, you can say I'm a jerk, that's cool. Add that hashtag so that people know, my team at home, that I was here and that I'm still alive. So what is Graal? Do people know what Graal is? Who thinks, Graal VM? Yeah, right, exactly. That's not it. So Graal VM, it's very unfortunate. I was talking to a few people outside already. It's very unfortunate. It's a marketing term that was introduced by Oracle Labs. Thank you very much for that. It will be difficult to drink with that thing on. So anyway, I was saying, Graal VM is basically a marketing term that, it's an umbrella marketing term that means 3 different technologies. Right? I think you mentioned it. You said, what have you been working on, Graal VM? And I said, I don't even know what you mean. And that's a problem. So Graal VM means 3 different technologies. One is called Graal. For a very long time it's called like this, Graal, and it's the JIT compiler, the Java Virtual Machine Just-in-Time Compiler. Then there's Truffle, and then there's Substrate VM. And Substrate VM is the thing that you might know today as native image. you know, the native compilation thing. I'm only talking about Graal, the JIT compiler, nothing else. Okay, so everyone knows what a Java virtual machine is. Who knows what a just-in-time compiler is? Okay, so we gotta explain that a little bit. So just-in-time compiler, the way the Java virtual machine works, since Java, I always say, again, I think you guys are all Java people, but when I say Java, I mean any language that is compiled down to Java bytecode and runs on the JVM. Could be Scala, could be Kotlin, you know, whatever. So a language like Java runs in a virtual machine in a managed runtime, and the way it works is you have an interpreter, and you can interpret the Java bytecode. But that's very slow, and then at some point you need a compiler to make your application actually run fast, so you need a just-in-time compiler to compile your code just in time during runtime. It's unlike an AOT compiler ahead of time, like a C++ compiler. Here we compile while we go. So if a method gets hot, because we've executed many times where it has loops, and so it uses a lot of CPU, we know that, the JVM knows that, notices that, schedules it for compilation, and then we get faster code. So Graal is actively developed by Oracle Labs. You might notice there's an official OpenJDK project for it. It's kind of stale, but it's still around. They put the source code on GitHub. Graal is using something called JVM CI, which was introduced in Java 9, JDK 9 under Chap 243, which is basically a Java virtual machine compiler interface. We actually call it Java level virtual machine, but whatever. And it's an interface. It's a Java interface that an external compiler can use, so you can plug it in. And Graal is basically that. Graal is written in Java. And so the one thing you want to take away from this talk today, besides free beer and pizza, is it's written in Java. And that's the main reason why I'm doing this talk, because the existing just-in-time compilers, maybe I should talk about this right now, because it will come up later. Do people know what C1 and C2 are? Ooh, not bad. So explain it. No, I'm kidding. So HotSpot, people know what HotSpot is. Yes, the Java virtual machine in OpenJDK. HotSpot has two just-in-time compilers. One is called C1, or client compiler, and the other one is called C2, or server compiler. You might know client and server from the -client -server command line options that we once had. They're not really useful anymore. But the difference is C1 is a high throughput compiler. So it doesn't do a lot of optimizations, it just wants to produce native code as quickly as it can. And C2, on the other hand, is a highly optimizing compiler that produces peak performance code. And in order to do this, it takes more time, right? It takes in profiling information that gets gathered during the run, and so on and so on. So these are the two compilers, and they are written in C++. But Graal is written in Java, and C++ and Java have very different properties at runtime. And that's, at this point in time, very important to understand and to know, to not make mistakes when you do benchmarks or run your application. So the way I do this talk is I have basically nothing prepared, and I do this talk in terms of I'll show you later. I'll fire up an empty Oracle Cloud instance that has nothing installed, no Java, nothing, and I hope it comes up. I gave a talk where it didn't. That was embarrassing. No, it will. But it's expiring on the 31st, so if I'm not quick enough, we'll see. So I'm firing up this instance, there's nothing installed, and I just download everything we need. So we're going to download JDK 11, OpenJDK 11, because it contains Graal, which I'm getting there in the next slide, no, the next bullet point down there. So where do you get Graal, or a JDK that can run Graal or has Graal in it, right? So there is Chap 295, ahead of time compilation. We've introduced ahead of time compilation in JDK 9, and you can use Graal already in JDK 9 on Linux because I made it so that you can, right? It's not really officially supported and people didn't know that it's possible, but I sneaked it in. And then with JDK 10, there was JEP 317, and then Oracle basically officially said, okay, there's an experimental Java-based JIT compiler, Graal, that you can use. But it's experimental. So that means you don't get support for it, right? If you get a bug, if you get a crash, yes, you can file a ticket, and they probably are going to fix it, but it's not the typical support you could get from Oracle, right? All right, so I have this very nice title of an Oracle Groundbreaker Ambassador. It used to be called Developers Champions. That was kind of nicer, but so I'm part of this program, and Oracle is giving me free cloud credits, so I can do this demo in the cloud, and so I like to do this, and we're going to do this now. So we go to cloudoracle.com. We hope that everything works fine, and we sign in as me. Yeah, so this talk is very boring because we're waiting always for things to download or for benchmarks to run to finish. Compute. Here we go, here we go. Yeah, why not? It's funny because I was on this page today before. Who the fuck knows? Which domain is this? I didn't kill that one, so okay, we'll see. I haven't created one of these in a long time, so we'll find Ordine, I think that's how you spell it. We put it in 82. Yeah, they change every time I do this, they change the UI. So virtual machine, yes. What can I get here? Okay, we take this one. We try to get as many cores as we can. Paste, yes, paste. So we need an SSH key. I'm also typing a lot during this talk, and typing in front of people is always tricky. Chris, this, subnet, yeah, looks good. Let's see what it does. So the one mistake I made, and I think it was GeekCon in Prague or something like this, I gave this presentation, and then because it always worked before, and so I just fired this thing up, and then I went back to the slides and I was talking about something else, and I didn't wait for this to turn green. So we have to wait for this to turn green. I'm not making the same mistake twice. So we're waiting for two things. We're waiting for a public IP address down here, and yes, and then for this to turn green, where it basically, it has to allocate a machine, and then it has to image the whole shit, and then it has to boot it up. When it's green, it's 99.9% sure it's coming up. When it's orange, we'll see. So this is the boring part, the waiting part. But we all have time, right? No one has to go home. There's still pizza left and beer, as far as I know. But come on. Exactly, I'm trying to, yes.
When you speak about the just-in-time compiler, you mean that's the place where it compiles the bytecode to machine code?
Correct.
And then you say it optimizes that compilation process. Can you actually see that difference? If I want to see, like, how is the machine code optimized? Can I see that sometimes this bytecode is optimized for this kind of machine code?
You can, yes, you can. How interested are you in compilers? You can. There's just no easy way to show that information because no one's really interested in it. So but you can compile stuff, and that then, especially with Graal, it's very easy. You can send all the intermediary steps. So do you know how a compiler works, kind of? So we grab this guy. I did not forget about you. this one. And so you parse code, Java bytecode or any source code into a tree, right? A tree of nodes, a compiler graph. And with Graal, the compiler, with C2 it works as well, but with Graal it's a little bit easier. You can fire up something that's called IGV. It's the Ideal Graph Visualizer. It's basically a UI tool where you can see the compiler graphs. And you can jump between the optimization phases. So you see compiler graphs because only at the very end of a compilation, you actually lower, that's what it's called, you lower the nodes in your graph into machine code. So all the optimizations in between happen on a graph. That's why I asked, how interested are you in?
Indeed, something I have to look into because I don't know that part about the nodes. I only know like the machine steps.
Yeah, one thing that's very easy that you can do is, I can show you that later, is you can compile a method and you can have HotSpot print it out for you when it's done. You see the final machine code, right? For example, if that's already interesting to you, you can do that. About me, I like to talk about myself. So I'm the Groundbreak ambassador, I told you this before. I'm working on JVMs for over 14 years now, pretty much always on compilers, so because I found it very interesting. GC is okay too, but sorry guys. Compilers is just so much more interesting, I think. So I used to work at Sun Microsystems and Oracle, always part of the HotSpot compiler team, so I was working on C1 and C2, mostly C2, a little bit C1. And I think the biggest project I've worked on was JSR 292. It's method handles, invoke dynamic. So support for dynamic languages in the JVM. I've done a lot of work there. I've written all the initial compiler support for it in C1 and C2. We had 2 different implementations of the whole thing, pretty much. One was very VM-centric, a lot of handwritten assembly code, super hard to maintain. And then we also had a performance issue with that, and so we moved a lot of that logic into Java, into the core library, into a package called Java Lang Invoke. And then I wrote a bunch of that Java code as well, method handle, lambda form, all that shit. So if it doesn't work, you could technically blame me. But a lot of people touched the code after me, so my code was fine. They broke it. So yeah, that was interesting. Then we did Chapter 243, the JVM CI that I was talking about earlier, Java level JVM Compiler Interface. We took basically Graal. At that point, they didn't have a very defined API. They had one, sure, they needed one, but it was not really defined. And so we said, let's take that out of Graal, make it an API. It's not an official API, obviously, right? But it's kind of stable, and put it in OpenJDK so that we can use an OpenJDK to work with Graal. That has a bunch of advantages. Mainly, if you download, for example, JDK 11 that has JVM CI in it, if you download Oracle JDK 11, you know it's TCK certified. You know that Java works, right? And if you work with Graal, let's say in a university academia setting or whatever, if it crashes, it's probably your fault. So that's the main advantage of the whole approach, right? You have a very stable certified Java JDK version, and then you can work on some experimental compiler on the side. 243 we mainly introduced at that point in time for Chapter 295, which is ahead of time compilation. I mentioned it also earlier. I'm not sure if anyone's ever tried it, but basically what it is it's a small command line utility that uses Graal as a code generating backend. So the utility basically takes a class file or a jar file, loads in the classes, sends over the methods to Graal, Graal compiles it, and then at the other end you get a shared library. And you can load the shared library into HotSpot, so it doesn't have to compile as much code. Sometimes it can improve startup, but not always. So it's very tricky to do AOT for a dynamic language like Java. At this point in time, I can say Substrate VM, right? Someone might have the question, what about Substrate VM? It's so fast. The difference is Substrate VM is not Java. It's a subset of Java. Very important, because if you have dynamic class loading, guess what? Substrate VM doesn't. And now I work at Twitter. Best company on the planet.
On the GSR 292,
Yes.
is that like allowing OpenGL to be run from Java? Like invoking, like there's a Java lightweight game library
No.
that calls OpenGL.
No.
That's not the same?
Why do you think that is the case? Supporting dynamically typed languages? No, it's more like to run, I don't know. Nashorn was implemented with Invoke Dynamic. To run JavaScript on the JVM, or to run Ruby on the JVM.
Not like C libraries.
No, 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 no. Okay. Why this talk? Yes. I kind of touched on this a little bit in the very beginning. So the main purpose of my talk is to get to try Graal. So you have to try it. Otherwise, you're not getting out of this room. If you have any project you're working on right now, I've asked the question earlier, what versions you use, which seems to be 8 at this point in time, and sometimes 7. So I'm not sure if you can run tests with 11, for example, or maybe you have some experimental instances internally, or maybe at the customer that you could run with 11. That would be very helpful, because, well, you know, that part might not be the case then, but if a customer of you would be using JDK 11, you could save him, that customer, some money, right, by not having as many instances. But more importantly, to fix bugs in Graal, because we want to make Graal a more stable, mature compiler. So one of the reasons why I went to Twitter was because I wanted to run Graal in a production environment. And I actually did, or we did find some bugs, and we fixed all of them. But since then, we've not found any new ones. So we need, as I always say, we need the shitty production code that you guys are writing. But in this case, it's what you're writing, actually. Usually I see the code you have, but you're actually producing it for your customers. And by shitty, I don't mean it's shit code. It's just very different than other code, right? I've heard that you use Spring, I think. So that already means that a lot of the base layer is the same, and you probably find new problems there. So we have that at Twitter too. We have a framework called Finatra, where basically all of our microservices are built on top, and then on top of Netty, right? So that stack is already the same for everything. And so it runs the same code over and over and over again. You're not going to find new bugs running this stuff. So everything that's new, and if you only run it once or twice, it would be, you know, hugely helpful. Mainly, if it runs better, cool, excellent. If it runs faster, that's great. If it runs slower, it would be nice to report it. But if it crashes, that's actually what we want. I want it to crash because then we found a bug. And then we want to improve Graal as well. So we want Graal, especially I want that. I want Graal to replace C2 in OpenJDK. And for this, we need it to be at least on par with C2 or better. Because you're not going to change. If it's about the same performance, no one will change, right? Why would you? Why change a running system? But if it's better, then people might. So, and then when I give my other talks and tell people how cool it is and how much money we're saving at Twitter by doing it, some people come up to me and ask me, is it safe to use because it's an experimental compiler? I can tell you, yes, it is. We have our own data centers. They're still up and running. They're not on fire. Everything's cool. If you're using Twitter, the tweet service and a bunch of other services, but especially the tweet service, runs for more than 1.5 years now, 100% on Graal in production. So everything you read and write on Twitter, all the other 20 million people that tweet every day, it's all through code compiled by Graal. And we've not had a single problem in the 1.5 years. So yes, it's very safe to use. How do I use it? Where do I get it? Exactly for these 2 questions I did this talk. And then when they actually try it, they sometimes send me emails and said, you know, they've run their favorite benchmark they've been using for 10 years already, and then they say, well, Graal sucks. And that's mainly because they don't know the difference between C2 and Graal. And that comes back to the one slide I had earlier, the difference between C++ and Java. Memory allocation is different. Bootstrapping, we'll be talking about bootstrapping, what is that? So you have to notice. If you know, then you understand how to interpret the benchmark numbers. Otherwise, things like that happen. And this happened. I got an email from an engineer of a very well-known company saying this is ridiculous. So, want to know more about the saving part? There's a talk, Twitter's Quest for Holy Grail Runtime, YouTube, you can watch that. Then there's a newer one about autotune where we save even more. I can show you at least the most important slides later, so you don't have to sit through an hour of me talking and bragging about myself. So back to the demo. Should be up by now. See? Yes, I want to log in. Here we go. This one and this one. We have two windows. Everyone can see. Perfect. We're having two windows because we're going to compare C2 with Graal later, benchmark runs and so on. First thing you will notice is completely empty. It doesn't even have, what a surprise. So we're going to install Git here, and over here, we're downloading JDK Java 11 because we're doing bleeding edge stuff here. No one's running on 8 or 7 anymore. Am I right? Exactly. So this is the part where we have to wait for things to download. Takes about, what, 20 seconds. Everyone can have a sip of the very delicious premium pills. Yeah, no, it's not premium. Okay. Okay, almost there. Perfect. And so we unzip this guy. And then we also need something that's called Scala da Capo benchmark. We're going to download that as well. And that one's pretty big, so I'm not sure how long that will take. Oh, see, very good connection. So then we're going to set Java home here, and we're going to put Java on the path. That's where the typing part comes in. Still cool. And in 30 minutes when I have downed that beer, it might be different, right? With like oh shit. So then same thing here. Here we go. And then we're going to set something that's called Java tool options. It's an environment variable that the JDK launchers pick up automatically. And we're going to, so the default GC since JDK 9 is G1. And we're going to look at GC logging output a little bit later. And G1 is just too complicated with the self-tuning heuristics and so on, and the output is just too hard to read. So we are going to use a more predictable GC, and so we use parallel GC. And we use a pretty small heap size, only of 512 megabytes. Oops. And the reason for this is the difference between C2 and Graal again. So Graal, since it's written in Java, it will use Java heap memory to do compilations. And that would mean if we run a benchmark that I'm talking about why I'm setting the start size to the maximum size of the heap, because the heap expansion would be different, right? With Graal, we would expand the heap much quicker than with C2, and so the GCs would happen at different times because it can allocate more memory. So we're setting it at the same start size so that we can sort of compare apples to apples. All right, good. Then, yeah, over here, I'm not quite there yet, actually, to be honest. So since JDK 9, we have Java modules, right? Everyone knows that. There are like 63 modules in the JDK as far as I remember. And we are going to look for modules that are called JDK internal.vm. And there are 3 of them, and one is called jdk.internal.vm.ci. That's the compiler interface. That's JVM CI. That's the Java part of JVM CI. There's obviously a big chunk of that is native code as well, because we have to talk to the VM. But this is the interface, the Java part. And then there's jdk.internal.vm.compiler. That's just Graal. It's basically a copy of GitHub Graal stuck into a module. That's all there is. All right, and then there's a management part, but that's not that important. Okay. Right. Here we go. So how do you use Graal? You need to get a JDK with Graal, obviously, or you could get a JDK with JVM CI and get your own Graal. So if there is a possibility, if someone's interested in this, there is a possibility to run Graal on 8 as well. It's just not that easy, let's put it this way. You could technically use Graal VM. There's a Graal VM binary download, right? But that means there's one problem with this. I don't really want to talk about it, but there are 2 different Graal versions. There's one called Basic Graal, or what they call now Community Edition, and then there's one called Enterprise Graal. If you download, I think there's a Community Edition binary as well. Download that one, because that one you can actually use. The other one, the Enterprise Graal, you're not allowed to use in production. And then you get into a legal issue with Oracle, you know, and then Ordina goes down and, you know, all that stuff. Because you're probably losing. So get a JDK with Graal. If you have that module, if it's, you know, JDK 11, for example, then yes, you're good. You're good to go. And then the only thing you have to do is to turn it on. And now we're going to look at how to turn it on. If we are going to chap 243. Okay. Are you sure? Not really. Yeah. See? All is good. So chap 243 introduced in 9, as you can see here, release 9. If you scroll all the way to the bottom of that chap, you can see how to turn on a JVM CI compiler. So you have to unlock experimental VM option because it's an experimental feature at this point in time. Then you tell the VM, please enable JVM CI. That does not automatically turn on the compiler. It just enables that you can access the interface. You can, and sometimes, for example, Truffle does that sometimes. It only enables JVM CI because Truffle uses JVM CI, but it's still in the background, it uses C2 to compile Java code. They do that sometimes. And then you say, yes, please use the JVM CI compiler. Then you're actually replacing C2 with Graal. And then there's a property called JVM CI.compiler where you could name the JVM CI compiler that the interface should use. If there would be more than one, you could pick which one you want to use. Today there's only one Graal, so we don't really have to specify that. Okay. So we copy these 3. Stick it in this guy. Copy it again. Here we go. Right. And then if you run java-version here, you can see it picks up these options and prints version. And then same over here. Picks up all these options and just prints out the version. So there is there's a flag, a hotspot flag called print flags final. It prints all the flags that hotspot has and all its values, and we are looking for JVM CI flags. So these are all the JVM CI flags that hotspot has. You can see enable JVM CI is true because we turned it on. Use JVM CI compiler is true because we turned it on. And I'm looking for this guy called JVM CI print properties. Here we go. And prints a long list of properties, Java properties, that you can set. So most of them are Graal related. And at the very top, there's a short list of JVM CI properties. So all the parameters that you pass to JVM CI and Graal, we decided to make them Java properties because they are written in Java, so it was easier to use Java properties to pass in things. So -XX is basically a Java property here, -D Graal dot for example. Okay, so I'm looking for this guy, JVM CI.initTimer, because it prints some debugging output when it initializes JVM CI. So we do dash capital D, JVM CI initTimer. We have to set it to true, Java property, and so on. Then we do a dash version, and nothing happens. Right? There's no additional output whatsoever. So did we do anything wrong? The answer is no. JVM CI is lazily initialized. JVM CI is only initialized if we actually have to compile a method with the top tier compiler. So here's, I think, the last question I'm going to ask today. Who knows what tiered compilation is? Tiered compilation. No, the people behind the, no. You remember when I talked about C1 and C2, that there are two different compilers? So what HotSpot does, and other JVMs as well, is you have different optimization levels in your JVM. So when you execute code, first you interpret it in the interpreter, it's very slow. Then you there are 5-ish, but actually only 4 tier compilation levels in HotSpot. 0 would be interpreted, but we don't really count that. 1, 2, 3 are C1 compilation levels, and depending on the level, how much profiling information we gather with the compiled code. And then tier 4 is the top tier peak optimizing level. Basically, it's C2 or Graal. Okay. So if we run this again and we do a print compilation here, you can see all the methods that are getting compiled for just doing a dash version. It executes a little bit of Java code. So the third column here, this guy, is the tier level. And as you can see, there's no tier 4 compilation. So no code gets hot enough to actually trigger a tier 4 compilation. That's why JVM CI is not being initialized. Good. So what are we doing about this? We are going to run the Scala benchmark thingy with a dash L. And basically the only thing it does is it prints all the benchmarks it has. That's all, right? But it executes a little more Java code than dash version does. So if we do this, you can see that. That was actually more than I expected. Let's try that again. All right, whatever. That never happened before. Sucks, but it's okay. So as you can see, we're initializing a class called HotSpot JVM CI runtime. And then it does a bunch of things. You know, it finds AMD64 and initializes some, you know, API stuff. And then down here, it's done initializing it in 58 milliseconds. Then there's this thing called compiler configuration factory that basically selects the compiler, which the property we had before would be that, but it's just automatically selecting the one it has, Graal. And then it prints stuff, but it's still kind of initializing things. So there is HotSpot Graal runtime because it found Graal, so it initializes Graal, creates the backend for our CPU architecture and everything else, and then it's done down here. It's actually pretty nice because that rarely happens, that we can see the whole thing initialize for some other reasons I'm not going into now. Yes, that's all I wanted to show you, I think, because if we go back, we have to talk about, before I go and show you the next, you know, output on what we're going to run, we have to talk about bootstrapping. So Graal is just another Java application running in your JVM. So you're running your JVM, you're running your application, but Graal is also Java code, so it runs too. That means it has to load Java classes for Graal itself. These Java classes, they have methods, obviously, which at some point need to be compiled because you want your compiler to be fast. You don't want to sit around and wait for your compiler being interpreted and compiling your application. That would be stupid. Yeah, exactly. So that is bootstrapping. So let me show you this. You can do, don't really ever do this, but you can do an explicit bootstrap by telling JVM CI to do it. This is only helpful in one instance, and it can be helpful running benchmarks. But most of the time, you don't have to do it. Okay, so let's go. Let's see how long that takes. I'll drink beer in the meantime. Premium. Okay, here we go, 18 seconds. That's nice. For running a small command line utility, waiting 18 seconds to come up. Yeah, no, it's not that bad. That's really the worst case. That's why I say don't ever do an explicit Bootstrap. I'm only doing this to show you it's compiling roughly 2,800 methods for Graal in that setup. We could only, while I'm talking, I could actually do this. I could turn off tier compilation, and that would be a true Bootstrap. Now Graal is compiling itself with itself. Before it was compiling it with C1, but now it's compiling itself with itself. And that takes much longer. And so what I want to show you here is you have to compile quite a bit for Graal. Technically, you could AOT compile it, right? And that's actually possible if I had enough time, and that would take actually too long now. We could AOT compile the Graal module and the JVM CI module and so on, and then this whole bootstrapping part would go away. But that's cool when you run on JDK 11, which I'm sure all your customers request, right? They come and say, hey, can you write us something? We want to run on 11 because it's so cool. No one does that. Everyone is on 8, including us. Twitter runs on 8. So what we did at Twitter was we backported all of this. We backported JVM CI, we have our own copy of Graal, and we run on 8, and on 8 there's no AOT. So how long did it take? 66 seconds. Nice. And it compiled roughly 4,800 methods. That's actually important. So if you run something big, like let's say a Twitter service, you compile about 5,000 additional methods of Graal. But it doesn't take 65 seconds. That's the whole point here. So this is the explicit bootstrapping where you tell it just do it. Actually, oh yeah, the way it does this is it takes Java-Lang object, the class, takes all the methods object has, which I think are 5, and they're all very small, and it schedules them for compilation. And while it compiles them, everything else of HotSpot gets so hot that it gets compiled. And then it compiles more and more and more and more. That's how you end up there. Okay, but that's basically what happens when you run something. Good. Bootstrap. And the Bootstrap, yes. Yeah, I always forget to mention this one. So bootstrapping compiles a lot of methods. Tiered about 2,500, but eventually it will compile about 4,800. You can do it either upfront, don't do that, or on demand during runtime. And on demand during runtime means it just compiles in the background like everything else. You have multiple cores on your machine. You have a number of GC threads that do GCs in parallel. You have a number of compiler threads that do compilation in parallel in the background while you run your application. So that's why this is not an issue, and I'm going to show you a little bit I think in a few minutes why. And then by default, like these on-demand in the background compilations, Graal is only compiled by C1. So Graal method themselves are only compiled by C1. And the reason we made this choice is we don't want your application methods to race, to fight for the first place in the compilation queue with Graal methods. Because it's a kind of a trade-off. Do I want my application method to be compiled first, but then the compiler will be slower, or should I compile my compiler now, but wait, you know what I'm saying? So C1 is so fast, it just spits out the code, and then you can run at a decent speed. Yeah. I think I forgot something. Let me show you this now. Why not? So let's run a benchmark that's called Aurora. And we do 3 iterations of this benchmark. It's pretty small. It runs for about 3-4 seconds or something. And we're going to use this a few more times to show a few things. 4, 3.9, 4.1, well, whatever. So it's roughly 4 seconds that the benchmark takes. And you can see the first run was a little bit slower. Maybe I could rerun it because things were still cold, right? You'd load stuff in from disk and so on. Things are getting initialized. So this is one run, as you can see. It's not forking a JVM, it's one run. So then things are compiled in the VM. So that's why subsequent runs are slightly faster. If you run this with Graal, it looks like this. .4. And then the next one is probably 4.0. 4.1. Ah, that's actually very good. So as you can see, the last run, the third, is about the same performance. The second one, yeah, you could get, okay, it's slightly slower maybe. The first one is what, 900 milliseconds, so almost a second slower than with C2. But far away from 18 seconds or 66, right? That's the point I want to make. If you run things, and we run here for, how much is this? 12 seconds, something like this, right? All the compilations that are happening, almost all of them, depending on the size of your application, obviously, but in the first 30 to a minute, if it's a bigger application, 99% of your compilations happen in the first 30 seconds or 60 seconds. And you can perfectly see this here. It just compiles all the stuff it needs at the very beginning in the background when you have all these spare CPU cycles laying around with cores you don't need at this point in time because you're not even garbage collecting stuff because your heap is not even full or whatever. This background compilation stuff, it only takes like an additional second. And I'm not sure how many Graal methods we compile at this point in time, but it's not getting more, right? Graal doesn't recompile itself all the time. It's just you have one additional second in the startup. Probably it's not going to hurt anyone. So that's the way we run it at Twitter. We don't do EOT, as I said, because we own 8, so we can't. It's not a big hit. Right? We save so much more time later in the game than this additional second at the very beginning. It doesn't even matter. And no customer would ever notice. Okay. So now let me talk about Java heap usage. Because Graal is, who paid attention? Yeah, well, better, that's actually, I should put better here, yes. But it's written in Java. What does that mean? All the application methods that we compile with Graal will use Java heap memory for that. As I talked earlier about compiler graphs can get big. Usually they are not. So usually they're around average, I would say, in the 5 to 10 megabyte range maybe. But they can grow big. If you inline a lot, if you do a lot of loop unrolling and so on, compiler graphs can grow into the biggest I've ever seen in my life, and that was, certainly an outlier at Oracle, was a compilation, a C2 compilation that took 1 gigabyte of memory. They can grow big. So you have to know that it's using Java heap memory. Potentially Graal methods too, but as I said, we're compiling it only with C1 that still uses native malloc memory. So that's not really the case, but everything your application or benchmark is using Java heap memory. So let me show you this real quick. We're using the same benchmark, and now comes the GC logging, so we turn this on. And so Aurora is a very small, very compute-intense benchmark. It doesn't do a lot of allocations, but that's perfect for this example here and what I want to show you. So we do 3 iterations. You see the benchmark harness does a system GC before and after a run to clean up the heap. And then, as you can see, during the benchmark run, there's no garbage collection happening. We allocate roughly 40 megabytes in a run, 30 to 40 megs, and then we collect that away. If we run it over here with Graal, it looks like this. And you can see, all right, yes, we are collecting. So we allocate 130 megs, collect down, 138 collect down, and then after the run, there's still 83 megs on the heap, collect down. After the second run, we have about 130 megs on the heap, collect. And in the third run, there is no GC happening anymore. So I mean, I could do 4 or 5 runs actually, why not? I've never done 5, let's see what's happening. Maybe I'm always lying. But as I told you, and as you can see at the runtime of the benchmark, we have most of the compilations in the first 5 seconds, then a few in the next 4 or something, and then there's nothing. Right? I mean, maybe almost nothing, because we have like 51 after this one. But we, you know, if there's a compilation happening every now and then, that's totally fine. The same happens with C2 as well. And yes, maybe at this point I should say, because I say it's happening with C2 as well, the memory that's being used to do compilations will be used anyway. In a container world, as we all are in today, and we are running this shit on a container right now, your container has, I don't know, 8 gigabytes of memory, okay? And then you have to size, right? You can give maybe 6 to your JVM, and then you need some spare on the side for all the metadata you're loading, all the classes. No one ever thinks about the compilations that need to happen, but they do, right? You need to have memory set aside for compilations that are happening. And remember, you know, again, outliers, but compilations happening in parallel, right? Especially at the very beginning. So if 2, 3 compilations at the same time use 100 megs, 300, you need that. Otherwise, your container is dead. It will get shut down. The case that will happen with Graal, if you're not using too much memory, we'll just collect it and, you know, and go on. And the important part here is, if you're not, I'll say that later. The important part here is, since you're not doing C2 compilations, and C1 compilations are much smaller than C2s, you could technically give your JVM more heap memory, right? You could take that 300, 400 megs that you have on the side for C2 compilations, you could give it your Java heap. And as I said, all the compilations are happening at the very beginning of your run, when your application is not fully up yet, right? Your application comes up, loads all the classes, blah, 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 blah. Especially in a microservice environment, as we are in Twitter, it makes a lot of connections to other services, takes some time, then it maybe does a tiny little warm-up loop, as some of our microservices do. Then it's ready for production services, for production traffic. At that time, all your compilations are done. And only then you actually need all of your whatever, how big your Java heap is, right? So this whole thing that that Graal will interfere with your application because it uses Java memory, it's not really the case. What could happen theoretically, I've never seen it happen at Twitter, 0 times, is you tune your service to exactly how much your Java heap memory is, less 1 megabyte, right? Tiny little bit of free space, and then a big compilation comes in. You get an out-of-memory error, true. And if you're lucky, it ends up on a compiler thread, which is very unlikely. It probably will happen in your application. And your application is not really written to handle out-of-memory errors, so it might go down. But again, I've never seen this happen, not a single time. And we run this for a very long time, and we deploy the tweet service and all the other services we have multiple times a week. Thousands of instances compiled that way. Never happened. Good. Very dramatic. So Graal uses Java heap memory, yes. There is no heap isolation yet. So there will be at some point. There is a project called libgraal, and basically what Oracle Labs combined with Oracle, the Java Platform Group, what they are trying to do is use Substrate VM to AOT compile Graal. And what that would mean is, because Substrate VM has its own heap, it would not interfere with your application. I think that's the wrong approach, but since I'm not working at Oracle anymore, my opinion doesn't have as much weight anymore, but I complained. Last year at FOSDEM, I complained very loudly because I think it's the wrong direction. Because it's the same as before, and the GC in Substrate VM is really shitty. They promised me you work on a new one, I know. We'll see how that goes. Anyway, most Graal memory usage during startup, I said that all the compilations happening in the very beginning when your application is not fully up yet, so you should, if you have a problem like this, let me know. I would like to hear about it. Memory is used anyway, either malloc or Java heap. You're going to use it. Okay, so yeah, now you know most of what you should know. And running on bleeding edge, so let's try that. That should work actually. So what we're trying to do now is we just build upstream Graal and then run the newest version of Graal on JDK 11. We'll see. We'll see if it works or not. Did it earlier today, but might not work now. Yeah, otherwise it wouldn't be fun. So we're cloning this guy. We're cloning Graal. Hey. And yeah, the beer kicks in. And we're cloning only a depth of 1 because it would take forever to clone that thing. It grew in size. That's why if tip doesn't build, we're fucked. Then we need something called MX. MX is, it's a blessing and a curse at the same time. No, not that, not that. It's a huge Python script that Graal uses as its build system and everything system. So it's like a 21,000 lines of Python script that I hate with my guts because I don't understand it. But you can do everything with it. And the main reason, I understand why they did it. So Oracle Labs was, Graal came out of JKU, that's a university in Linz in Austria. And they have a very close collaboration going on with Oracle Labs. And so there's still many students working on Graal doing their thesis. And for them, with MX, you can do everything. You can clone the source code, you update the source code, you build, you run, you generate your IDE configuration files, everything through MX. So for new people coming in, it's very helpful so that they don't have to understand all the shit behind OpenJDK and everything complicated and built blah, blah, blah. So it's good, but I hate it. Okay, so let's put it on the path because Graal needs it. And then in Graal here, you can see the it contains all the other projects. So there's Substrate VM, for example, there's Truffle, there's Sulong, I'm not sure if you heard about this. No, I'm not going into it. And then there's the compiler. There you go, compiler and MX. There you go. We can do a clean if we want to. And then we do MX build. And today, unbelievable, there's an option called no native. Otherwise, I mean, now I can explain why I'm using no native. There's a small part that Graal builds. It downloads a bunch of dependencies, as you can see, and then it builds code. There's a small part that's written in C. It's for Truffle, so that Truffle can call out to native libraries or something like this. libffi, I think it's using libffi for stuff. And as you might remember, the container that I just fired up didn't have Java installed and Git installed. So do you think it has GCC installed? Of course not. That's why the native build fails, right? But we don't need that. We only need the Java part. All right, path. And here we go. And Graal compiler. Yes, and that should be done in shortly. Takes about, I don't know, 30 seconds, a minute to build the whole thing. Time to drink some Belgian beer. Okay, soon. Graal Truffle runtime. We need something that's called archiving Graal. Yeah, there you go. All right. So, building Java module, because we're building with JDK 11, so it's building a modular jar file out of Graal.
Why no Maven? Is it possible?
I'm sure it is. Hey, send all your questions to the GitHub. Hey, I'm not affiliated with that. Okay, here we go. So, as I said, MX is used for everything, so you can also run Graal through it. So, if you do MX VM, it's basically just running the VM. A -v is just verbose, so we can kind of see what's happening. And as you can see here, it's running Java, right? Enables JVM CI and so on, and then it does an upgrade module path with this guy. That's the modular jar of Graal that we just built. And if we are running, what are we running? Yeah, why not this? And then we do an xlog class load. Yes, that's true. I totally believe that. So all the Oracle Graal compiler classes are loaded from JRT, which is the internal file system name for the internal file system for modules. And so we are loading from this jdk.internal.vm compiler, the module we've seen before. All the classes are being loaded from there. If we run the same command, not Java, but mxvm, you can see that all this stuff is loaded from this file. So the modular jar file gets picked up, and then we just use the latest bleeding edge Graal thing that there is. And then we can do remove that. Too much output, and run a benchmark. And I've done this talk many times, and I'm always hoping that the benchmark will be faster, and it never is. I think it's just the way it's written, it's just too much, you know, integer adding and subtracting whatever it's doing. I don't know. See, it's about the same. But this was run on the latest version. So you can now, number one, it's very easy to do. I did nothing. I just cloned it and built it with that one command. You can now do an MX IDE init. I'm not sure what it does here. It probably doesn't work, but it does a bunch of things like it right. It creates a bunch of Eclipse project files and IntelliJ project files and blah, blah, blah. You just open it up in your IDE and then you hack on it, right? It's very easy because it's written in Java. Hacking around in C2, different story, right? And the good thing here is you press save, you have a fucking modular jar file and you run it. Right? That's all you have to do. C2, make, C++, waiting for the whole thing to link, build an image, blah, blah, blah. It takes forever. This is perfect for, you know, academia, people who are doing compiler research and so on. Excellent. So, yeah, this one doesn't build. I tried today. I can't get it to build. The reason is this would be a demo that I like to show. That additional time of the bootstrapping disappears in the startup noise, which we kind of already saw before with that very short benchmark, but here it would be more obvious. So what I would be running would be a thing that's called Twitter clone. It's a very small implementation of Twitter on top of Finatra. That's that open source framework we use. And then you can see this, you know, it starts up in what, 12 seconds or whatever it does, and it's basically, it disappears in the startup noise to put the bootstrapping overhead. But I can't do it, doesn't work. Scala demo, much more interesting, because it's impressive. Okay. Yes, first things first, we're going to increase our heap size, because otherwise we get too many collections. We do 2 gigabytes, and then we run this guy, no, not this guy, and we only do 2, otherwise it takes too long. A default size of a benchmark called factory. Here we go. That should run. And then we do the 2 gigabytes here as well. Yes, here we go. Gig. Perfect. And yes, I forgot something. Thank you for telling me. We want to see GC. Okay. So if I go back here, you can go up to benchmarks, and then you see all the benchmarks it has, and there's a benchmark called Factory. It's called, or it is, a toolkit for deployable probabilistic modeling to extract topics using latent Dirichlet allocation. I have no fucking clue what it is. I have really no idea. I gave a presentation some time ago, and after my talk, a guy came up to me and said, "Oh yeah, we're using LDA." What the fuck are you talking about? So, turns out they're using LDA. There's latent at their company. I don't know what it is, but it's a very good benchmark to show you what I want to show you. So this was the warm-up, and we're just waiting for this one to finish. It takes about 25 seconds, I think. Let's see, depending on the machine. Come on. Yes, 36, okay. Slower machine, doesn't matter. We all have time. So we're running the same thing over here. As you can see, just by the length of GCs, the warm-up just does a little more GCs because it compiles stuff and then it builds up some data structure. I don't actually know why it's doing more, to be honest. I should not try to explain it. But the important part here is it's starting at GC 54 and it ends at 95-ish. So we are doing roughly 40 GCs. And as you can see, we allocate about 750 megabytes and then collect down to 74 all the time. And this takes 36 seconds. As you can already see over there, we're already done, and the run was only 15 seconds. Okay, I mean, that's a huge improvement. And the reason why it's so much faster is, as it's also very clear to see, it's only doing half of the GCs. It's only doing 20 GCs over there, also roughly 700 megs, collecting down to 81. The reason for this is why Twitter's saving so much money. The reason is two major optimizations, compiler optimizations, are better in Graal than they are in C2. And one is called inlining. Most people know inlining. And then there's one called escape analysis. And escape analysis can get rid of temporary objects allocations that you don't need. And this benchmark is written in Scala. And Scala does a lot of memory allocations that are not needed. And Twitter's microservices are almost all of them written in Scala. That's why we save so much. It can eliminate so much garbage, allocations that we don't use in this benchmark that is just needing half of the GC cycles. This means, you know, I mean, they don't take too long, but if you look at the GC times here compared to these over there, they're also shorter. And if you don't have to allocate the memory, you have to execute less code, because allocating memory takes up some code. That means your code is tighter, and that means your compiler graphs, when your compile methods are smaller, you can inline more. That means your code gets faster. That's exactly what's happening here. And before I basically wrap this up, let me quickly show you this. Exactly that one. No, let me show you this one first. Where is it? This guy. Yeah, this actually, yes. So this is the tweet service. And I ran the tweet service for 24 hours. And these are garbage collection cycles. You know, it's PS scavenge cycle, so it's using parallel GC. And we can reduce GC cycles by 3.4%, which is far away from the 50 we've just seen, right? But I used this factory benchmark to look good on stage, right? Everyone is impressed. I saw like jaws dropping and shit. 3.4, you would be, yeah, I don't know, get the guy out of here. It's not great, but it's still good, right? It's still doing the same amount of work. still, sending out the same amount of tweets, but using 3.4% less GC cycles, which means if you don't do GCs, it always improves your latency, because GC cycles always affect your latency. So let me skip this auto-tune part, because the only thing I want to show you, and you've already seen it, is this guy. That's the CPU utilization reduction that we see. This is because, so we use, in this experimental setting, in production it's slightly less than that, but let's say 10, okay? We reduce CPU utilization by 10%, still processing the same amount of tweets. That's a combination of reduced memory allocation and better code. And this means Twitter needs 10% less machines to do the same amount of work. And that's a lot of money. And that's the money-saving part that I was talking to about at the very beginning. If you can use something like this, you save a shit ton of money, and we do. I can tell you how much it is, but it's a lot. Yeah, that was, that's all I wanted to show you. I can show you, yeah, let me show you this one as well. It has the auto-tune thing in it as well. That's P99 latencies for the tweet service. It's a little hard to see how much it is here, but this is basically, yeah, it's hard to say. But this is auto-tune, ignore that for now. But I basically integrated over all the GC pause times. So we have a sum of all the pause times over 24 hours. And just by using Graal, C2 is blue and orange is Graal, we reduce latencies by 20%. And so that means if you open up your Twitter, you get your tweets 20% faster. At the same time saving money. Yeah, good. The summary of my talk, and I'm done here now, I haven't even finished my beer yet, is this. That's all I want you to do. Try it. It doesn't hurt, as long as your machine doesn't go up in flames. But give it a shot. If it runs better, as it does for you, does for us, great. Let me know. If it doesn't run slower, would be very interesting to see. Why not? It's very likely that it's code that's proprietary, so we probably can take a look at it, but maybe we'll find we can extract a test case, or I don't know what, to figure out what the issue is. Would be great. We can improve Graal. Or if it crashes, as I said before, perfect. Bug found. We fixed it, hopefully. And one of the main reasons why I'm touring around and talking to all you people and all the other people, and I want you to try this, is I'd rather have you find a bug than me getting paged that Twitter doesn't work. That would be bad. Okay, that was all. Thank you very much. Yes.
I heard Oleg talk about it in the DevOps. He said that functional code will be optimized usually better than older legacy non-functional code. Is it the same reason why?
Yeah, pretty much. Yeah, the thing I left out is, I said this in one of my other talks, with Java code, and unfortunately you were a Java shop. Yeah, I didn't see it. Java's been around for a long time, so we use Scala, for example. So there are two reasons. Scala is more functional, yes, and so it allocates all these temporary objects, and if you look at the Java bytecode that Scala C produces compared to what Java C produces, it's not really a technical and not the right thing to call it that way, but I always say that Java C bytecode is more static, flat, while Scala's is very convoluted and complicated. If you ever have time for an hour or two, try to figure out how the main method in a Scala hello world gets called. It's ridiculous. So, but that's one reason. The other reason is why something like Scala, I haven't tried Kotlin enough, but Kotlin's very similar to Java in terms of bytecode. HotSpot and C2 have been optimized for 15 years to run Java code. We've never invested 1 single minute to optimize for Scala code at Oracle. So it's been a finely tuned machine for Java code. But more importantly, all the Java code you people write is tuned for C2. All the method sizes, you write it exactly that way that it runs the fastest on C2. And it's very difficult to come in with another compiler and make it better. So these are 2 reasons why, but the thing with the garbage collection and escape analysis, that's mainly what he was talking about, yes. More questions? Before the surprise? Yeah, we can chat later anyway. All right, cool, thank you.